Okay, I was going to just mention one thing for the benefit of Don Holk and Al Osmar and some of the other guys in Division 2123 that we work with, is that we normally think of microwave semiconductor devices as being special devices. At least that's what everyone else seems to think. We who work with them don't look at them that way. Actually, we think we're doing the whole job. They're getting away with operating at low frequencies, DC essentially, and so they don't have to worry about all the when he shows up.
Start it again.
Oh, I will. I'll have to start this over.
I'm going to leave.
I was saying that we who work with the microwave devices don't think of these devices as being special devices, which seems to be a kind of a connotation that everyone seems to put on these. We think that we're doing the complete job, whereas the guys who work on the low frequency devices are actually just doing part of a job. They can get away with assuming that a length of wire is simply a series inductor at low frequency. We know that it's actually a piece of transmission line, and we have to consider it that way. We also know, take for example, the small signal current gain of a transistor, H, little HFE, whatever symbology you want to use. We know that that's a complex number. In other words, it has a magnitude and it has a phase associated with it, and you have to consider that. But at low frequency, they can more or less get away with considering it to be just a scalar value, just a magnitude. They can ignore the phase. Let me get my notes here. One of the things I want to do is kind of give you an outline of what I'm going to talk about. Just briefly, time permitting, we can go through most of this. Kind of give you a definition of microwave devices. I don't think there's a written or printed definition anywhere in the industry.
Do you want to pass those up?
Yeah, I will in just a second. Then I'm going to talk about the various types of devices. We're not going to go into them in any kind of depth because that would take like 3.5 years. But we'll talk about them on the surface, kind of a cursory type of approach. And I also have to talk about the applications on many of these devices because they're so geared to application. In other words, the device is so general it can be used for different things of the same structure. But because of the application, the device is tailored to that application, makes it a special device, and we give it a special name. Then hopefully we'll have time to talk about how they're packaged, and I've got some devices to show you so you can actually have hands-on and see what we're talking about. Talk about beam lead devices. Microwave devices seem to be the only area that will continue to use beam lead devices because of their unique construction. They don't give us a reliability problem. And then maybe we'll talk a little bit about testing and characterization. You can understand what we have to go through to test a microwave device. And if there's some time, I have a little short slide that will kind of give you a good, bad, poor type evaluation of radiation hardness, these different types of microwave devices. I have here a test. Take 10 minutes and fill this out. You can pass those out. What they are is just, in essence, some of the notes. They're by no means complete. And if you do want a completed copy of the notes, please indicate so to me before you leave. I just didn't get them all typed up on the word processor. So, okay. Okay, we're about page 3 on that. I've just reproduced the slides for you to go by. The definition that I give a microwave semiconductor device is any semiconductor device which is capable of operating in some useful mode at microwave frequencies. That mode may not be its obvious mode. Okay, for instance, a PN junction may not work in microwaves as a rectifier, but there's some characteristic of that PN junction that's optimized to make it usable at microwave frequencies. Okay, distinguishing properties. Almost always, I say almost, there's always an exception to the rule. Microwave semiconductors are very highly doped devices. There are a few exceptions to that, but I mean, generally this you can tell when you perform DC and RF parameter tests on the device that it is a microwave device. Another thing, if you look at it physically, if you open the package and you look at the die or do cross sections, you will see very fine geometries, very small. They're scaled down versions of the low frequency devices in many cases. And the other thing that gives them away is the type of packaging, which we'll show you later. They use a strip line or a waveguide or tune cavity, whatever you want to call it, type of package. And these are very expensive packages. And at low frequency, there'd be no reason to use them. But as you get into higher frequency, they tend to minimize parasitics, and I'll talk about that a little later. First of all, you might want to know what's a microwave. You know, that'd be nice. I don't know if you can see this or not. This is the only printed definition I can. That's upside down. It's upside down. The print is so fine. You can probably read this better on your copies. But what we're talking about, and this is the only printed definition, I'll say that again, I'll reiterate it, is anything from 1,000 millimeters to 1 millimeter in wavelength, or about 300 megahertz to 300 gigahertz, and I'll qualify that, is considered microwaves. This is the only printed definition I've ever found. Actually, we're going to talk about a device that's used to clear up to 400 gigahertz, been demonstrated up to 400 gigahertz, and the National Bureau of Standards has done some measurements up to 700 gigahertz, I think, or 900, I can't remember exactly. So where you define microwaves is probably arbitrary. I think we tend to talk about it being anything a gigahertz or above. But for this presentation, I'm going to talk about some devices that are less than a gigahertz. Okay, you sometimes hear us talk about frequency bands. There's a new set, which they've done it very logically, but nobody ever uses it as far as I know. That's called the A, B, C, D, E, F, G bands. Just take an example. We talk a lot about L band, S band, X band, KU band. You'll hear us talk about these. Well, that's what it translates into frequencies. And then, like the K band is not broken up on this slide, but the K band is actually broke up into KI and KU band. All these other bands are shown here and how they're broken up, so you can see all kinds of designations. And I guess typically we fall into the habit of talking L band or S band or whatever, and it really isn't a good explanation of the frequency. I think a lot of us were surprised to find out, I think Marcelino Armendaris would agree with me, that that's 390 to 1.55. But nevertheless, I found that in several texts, so that must be the right definition for L band. I always thought it was like a half to 1.5. But this is the only printed definition I've really found of these that is consistent. So we'll go by those definitions for now anyway. Okay, the actual types of devices themselves. Gee, if I covered all these in depth, like I say, it would take 3.5 weeks just to talk about them. Not to mention, I don't understand the solid-state physics fully on some of them myself, and I'll admit it. But some of the devices that we'll talk about are these top types of tunnel diodes. I'll talk a little bit, very little, about transistors. Tomorrow they're going to be talking about MOSFETs and other similar devices. And so I'll let them explain the structures and so forth. In fact, I'm not really going to go into the structures of these diodes that much and how the carriers flow and all that. Like I say, that would take 3.5 weeks. Now we're going to talk about the future of microwave devices, and I'll explain what that is a little later. Okay, a comment on PN diodes. Don Holk kind of said this the other day, and that's that these devices actually don't lend themselves to high-frequency operation in the role of a rectifier, or as we call detectors at microwave frequencies. And the reason for this is the so-called minority carrier lifetime or stored charge, reverse recovery effects of the diode causes a distortion and rectification as you go up into higher and higher frequency. So that's why I say low frequency rectifiers as an application, limiters and mixers. Now varactors are actually of a PN type of structure. They're usually very special PN structures. Some of them are PIN, we'll discuss that in a few minutes. So really, varactors is the only extension above, say, 1 gigahertz, actually above the UHF frequency band of the use of a PN diode. And I'll show you just some curves. I apologize for the quality of this slide, but it'll give you an idea. The top curve is an ordinary PN diode, and this is operating at 30 megahertz, which is lower than any of the frequencies I'm talking about, but it does exemplify what I'm talking about. The lower waveform is not an ideal waveform. It's actually a waveform of an RF diode called the Schottky barrier diode, which we're going to talk about. But this pulse gives distortion to the rectified waveform. That can cause problems in a microwave circuit. It also generates lots of harmonics of this 30 megahertz signal. And those harmonics can disrupt the operation of the microwave circuit. This is what we like to see. We want it to rectify efficiently, and so that would be a good rectifier. Okay. We do this with a device which uses an effect, or actually it's a metal semiconductor junction effect, which was named after Schottky, who was the first one to really explain the process and how it worked. Originally, this was called a hot carrier diode before being renamed Schottky barrier diodes. And we just usually say Schottky diodes instead of saying all the words Schottky barrier. But it's used as a detector. That's a rectifier in microwaves, and mixers and wave shaping, because it's a very, very, very fast diode. And the reason that the device is so fast is because it doesn't suffer from the minority carrier effects. It has no reverse recovery time, virtually no reverse recovery time, because it has no minority carriers that have to recombine when the diode is reverse biased. For years, we've actually had Schottky diodes available. They were in the form of a device called a point contact diode. What this is there's a small metal cat's whisker, or whisker, I guess it's a slang term for it, but it was a fine piece of filament wire that made contact with a small element of semiconductor, usually an N-type semiconductor. I guess the first ones, I really don't know what the first ones used. They used Gallia crystals, the real oldest, as far back as you can go, but certainly there were germanium. Those are still in existence today, and silicon, and there's even some gallium arsenide ones, I understand, although I've never seen one. The device has some problems in that it's not very reliable. It can't take a shock environment. Tend to break the cat's whisker off, whatever. They also tend to alloy and have a very short life after a while. The metal in contact with the semiconductor, they tend to like each other, and they tend to alloy, form a compound. So typically, you won't see these used at frequencies above a gigahertz. Instead, they go to a fabricated metal semiconductor device called a Schottky barrier diode. Okay, the advantages of going to this diode, you get better electrical characteristics. If we look at this waveform, we have a typical point contact diode, a 1N21G. And you can see this is the forward characteristic, and I think there's different scales on these. It's a tenth of a volt per division. So it has a rather low forward drop, which may be very useful in some applications. But it doesn't have much of a breakdown either by the same standpoint. So it's probably not a very high quality rectifier. On the other hand, a fabricated Schottky barrier diode has a much nicer characteristic. This one's about 35 volts breakdown, and what would that be about? That's less than 3/10, isn't it? That's a pretty good one. Forward bias is typically around 4/10 of a volt on most of them that we use here. What we get is a lower parasitic resistance of the diode by the fabricated device. We get lower noise generated by the device, and maybe we'll talk about that a little later. It's capable of operating at much higher power. It's another big benefit. And of course, the mechanical strength is a lot better. In essence, what the Schottky diode is and how it compares, I'm just showing this as a comparison to all the other slides you've seen on conduction and valence bands and within the semiconductor. We have a p-n junction again, but the p-n junction is formed by a metal and an n-type semiconductor. The reason that n-type is used, or the reason n-type is, I specify n-type, is because most of these devices are fabricated from silicon. And n-type silicon has a much higher mobility than p-type. But the device will work with p-type silicon just as well. So we actually have an anode and a cathode, where the anode now is the metal contact. And the main benefit of this device is that it is a majority carrier device. That means that electrons flow from the semiconductor into the metal is the primary function that controls the current through the diode. And simply all this slide is showing you is that right at the metal to n-type semiconductor interface, there's a built-in barrier potential, just like in the PN diode, but different in that this barrier potential is almost a function of the metal used. And so we can select the metal and control just what this voltage is. The slide we just saw before, it was less than 0.3 of a volt. And I think that was, it seems antimony was one of the materials in the substrate also. So yeah, I think it was gold on some sort of a gallium antimony, I believe. But that was probably what gave rise to a much lower barrier potential than, say, the diodes that we're used to using around here, which are gold on silicon, which is about 0.4 of a volt. What happens is as you go from the actual interface into the semiconductor, the conduction band and valence bands actually shift to a slightly lower level, with the Fermi energy again being in the forbidden gaps, more or less centered, equal charge, because we're all in one type of semiconductor. Okay, what happens is we forward bias this diode. Electrons now gain sufficient energy that they can overcome the potential barrier and flow into the metal. And this process continues as you increase the forward bias until it reaches the point where this line actually goes all the way to the top, and all the electrons in the conduction band, this conduction band, have enough energy that they flow into the metal. And then the only thing that limits current in the Schottky beyond this is the parasitic resistance in the Schottky. Now that's changed somewhat because this thing, this minority carrier thing, the holes from the metal into the semiconductor, still play some part in determining the current through the Schottky diode. But it's, for all practical purposes, if you operate the Schottky diode below this point, the point where all the electrons have enough energy to get into the metal, below the saturation point on the Schottky, you can ignore this hole diffusion, and the device is essentially a minority carrier device, majority carrier device, I'm sorry. So there's the benefit of that, no stored charge, no reverse recovery time. It's a very efficient rectifier. Okay, the second type of device is called a PIN diode, or in slang, a pin diode. Again, Don Hope talked about this device for low frequency. It certainly can be used at low frequency for the same reasons that we use it at microwave frequencies, except that the applications tend to group themselves into one of three. Either a modulator, it's where we do an amplitude modulation of an RF signal. Variable attenuator, we actually adjust the power by changing the bias on the diode. Our switches, we turn the power off and turn it back on. And really, these are all really the same thing. It's just a different way of implementing the bias currents that drive the diode. Okay, what a pin diode is, why it's called a PIN diode. Again, Don Hoke mentioned this. They put a layer of intrinsic semiconductor between two high conducting P and N layers. And what happens is, very generally, we increase the transit time that it takes the carriers in forward bias to travel from one side of the junction to the other. And this increases the carrier lifetime, tends to make the diode look like a low impedance. And as we increase the frequency, we put an RF swing voltage superimposed on the DC bias that's forward biasing this thing, it tends to look like a pure ohmic resistor. We reach an area called the threshold frequency where the diode actually stops rectifying like a PN diode and then begins to look like a pure resistance. The reason that it looks like a resistor, and let me catch up here in my notes, again, is the carriers take longer than the average carrier lifetime takes longer than the RF swing that we're applying during the forward bias part of the cycle. And for that matter, if the RF swing is less than the DC forward bias, so we always keep the diode forward biased even during the negative part of the cycle, we get the same effect. The RF swings faster than the carriers can move. And what happens is it then looks like an impedance to the path of the RF, and it's mostly resistive. And what happens then is that you end up with a device that is a DC current controlled resistor at RF. This is if you're above the threshold frequency where the RF is actually moving faster than the carriers can flow. And this is pretty typical. This is a Hewlett-Packard diode characteristic, but it seems to fit Unitrode and some of the other devices I've looked at. And you can see that at strong forward bias, the device looks like 1 ohm. Now remember this for a later discussion. And when the current is very small, it starts to approach 10,000 ohms. So we can use this property to, for instance, we could put this resistor in series with RF power in a circuit and attenuate that power. That means that the diode will hold off some of the RF power and become lossy, and so we don't transmit as much power through the pin diode. We can also shunt it to ground and bias the diode to a low impedance, 1 ohm, and what happens is we get the phenomena called reflection, where the RF power incident on the diode is reflected back and doesn't get to the circuit that's downline. So there's several ways to use the device. Generally, when it's used as a switch, it's reverse biased to turn the diode off, and it's hard forward bias, since it's DC wise, to turn the switch on. And you can see the benefits of the hard forward bias keeps this resistance way low. So that it essentially looks like a through switch. Although some relays don't have that lower resistance, by the way. Okay, another type of diode, which is really a pin diode, is a step recovery diode. This device has a very, very thin eye layer. And what it takes advantage of the parasitic that is found in the regular PN type junction, and of course it can be controlled in a PIN more, of the reverse recovery time. I'll go ahead and show you that the waveforms. SRD stands for step recovery time diode. That's generally the way they talk about them in the industry. We take a square wave signal in this circuit, series biased with the load, and we switch it. The diode will conduct in the forward direction for the period of the applied waveform. Then as the waveform suddenly switches, the diode switches, but because there's this reverse recovery time, the diode will conduct in the reverse direction, and this can be actually, this is shown that it's less current than in the forward direction, but by proper adjusting of the resistances, it can actually be made more current than was flown in the forward direction. But typically it can be equal to or less is a good rule of thumb. It will conduct for the time it takes all the carriers to recombine back in their original states, and this will happen, and rather abruptly the current will stop flowing, and the thing will look then like the normal reverse characteristic. It'll just revert to the reverse saturation current. Okay, well, the reason that we incorporate a very thin intrinsic layer in the diode, is to sharpen up this cliff where the current snaps back. In fact, there is a device called a snap diode, and a snap diode is really a pin diode. And I have to qualify that by saying maybe we go back to our original, very simple. That I've called this an intrinsic semiconductor, when in reality that's very difficult to make an intrinsic semiconductor. It's usually slightly doped, and on most of the RF pins it's an N- in the terminology that Bill Dawes was using the other day. This is very close to a snap diode, which is an N, so it would be a P plus N, N plus type of structure. So there really is very little difference, but a snap diode is considered to be a varactor diode, which we'll talk about in a second. So by intrinsic, we really don't lose anything. What we still do is we spread out the transit time that the carriers take to move across this junction, even in an N- semiconductor, so it works quite well. But it's easier to speak of it being purely intrinsic. Now what we can use the step recovery diode for, among other things, obviously we could use that square pulse to do some wave shaping, is we can use it to generate impulses that, I said before, the parasitic of the diode was we could produce all kinds of harmonics. It's exactly what this circuit does. They apply a sinusoid waveform, as shown here. This inductor sets the time constant of the circuit, and what happens is, as the swing is positive, of course, this should be a forward diode drop, the diode conducts. And we're supposed to assume there's been enough time for it to steady state. Then what happens is, as we start to swing negative, the diode starts to conduct in the negative direction while these carriers are being removed. And it'll reach the point where it snaps back. However, the inductor controls, the current can't change to an inductor instantaneously. So what happens is we see a sharp impulse across the output load. What happens, or what we find about this impulse is that it is rich in harmonics of this implied sine wave. So we can use this to generate higher frequencies from a lower frequency. And the device that does this is called a switching reactance multiplier. Here's our SRD and the output waveform. We send it through sort of like a bandpass filter that selects the frequency that we're interested in, but it contains sideband harmonics, so we run it through another filter to remove those, and we end up with a pure sinusoid out. And so as you can see by the period of the waveform, they're showing that we got frequency multiplication, harmonic generation, whatever you want to call it. And this is typically what they use a step recovery diode for in microwaves. Another variation of a pin diode is called a limiter. Now, a limiter diode, again, it's a PIN device, but again, it has a very thin I layer. And the reason for this is we try to make the diode a good rectifier at RF frequencies. And if the I region was too thick, it would be a poor rectifier, look like a pin diode, look like a resistor. Okay? So they make it thin intentionally to be a good rectifier. It's usually used in a circuit like this, which should explain how it works. What's really missing here is there should be a resistor to ground, which would be a very high resistance, and here this would be labeled a very low resistance, okay, with keeping that in mind. What happens is we can bias the diode to where it's just to the point of going in forward conduction, and we can vary this so that we can change the amount of added voltage it'll take to just start that device conducting, and then how far it goes into conduction. And the theory of how this works is we bring an RF signal in, and we get a summing. The DC power and the RF power coming in will reach, the RF power will add the necessary voltage to reach the threshold where this diode starts to conduct. Now remember, when this diode is in hard conduction, it's a very low impedance. When the diode is off, it represents a very high impedance to the circuit. So what happens is, as the RF power increases, the diode turns on harder, the impedance gets lower, and what happens is the RF power starts to get reflected because of the low impedance. It begins to look like a short circuit back at the source. And our load down at this end is protected from that high power signal. And we can control that threshold point just by changing this DC bias. As a matter of fact, we can ground this DC bias point and not give it any DC at all, in which case it takes more RF power to turn the diode on, but it will still turn on during the forward portion of the RF cycle. Now, even in that case, because of the stored charge effects, at least a portion of the reverse bias cycle, the negative cycle, negative swing of the RF, will conduct and look like a low impedance. So the device, even for a greater percentage of the time than 50%, will turn on hard and represent a low impedance to the circuit. And what that'll do is reduce the duty cycle of the RF power going to the load. And the load usually has a certain continuous power level rating that it can take. Say it's a receiver or something that's very sensitive, and it can only work at very low powers of microwatts. And we might have a TV signal out here that's at 100 megawatts coming in. And this poor little diode has got to limit that power to keep from burning up the front end of that receiver. And that's what a limiter does. Generally, most limiters for high power applications like that, there'll be 2 diodes. There's no advantage in going with 3. The first one will hog most of the power, and the second one cleans up what it couldn't handle. So a lot of times you'll see a limiter diode and it'll actually have 2 of these in a package. It's not unusual. Okay, another RF diode, quote unquote, is a varactor diode. This is a tuning diode. The device is usually usually reverse biased with a DC bias, and then the RF signal is superimposed on that in such a manner as it effectively the reverse DC bias dominates what the reverse capacitance of the diode is. And so now we have a voltage controlled capacitor, and it can actually tune the RF. It's usually put in the, for instance, the base emitter circuit of an oscillator transistor. And by adjusting the bias then that's on the base emitter, you also adjust the reverse bias on the varactor diode and changes capacitance, and that works into some sort of usually a tank circuit to tune the oscillator. Varactors are used, I mentioned a while ago, a snap diode is really a varactor diode. Well, that's because it's not intrinsic, it's N, it's more N than intrinsic, for example. And so there are applications where they're used in multipliers and harmonic generators and up-converter mixer. An up-converter mixer is nothing more than a mixer, and we replace a good detector diode in the mixer with a step recovery diode or a varactor diode for the purpose of generating harmonics. So that instead of coming out of the mixer with an expected intermediate frequency where you're mixing a local oscillator frequency and an RF frequency and coming up with an IF frequency, instead of coming out with lower IF frequencies, you come out with much higher frequencies and actually up-convert or harmonic generate or frequency multiply. It's all the same terms. So really, all of this is really just one application. But the biggest thing that we use them for here at Sandia, and we do use varactor diodes, is for voltage-controlled oscillators. Now, a varactor diode can also be a pin diode. And I was talking to Charlie McCarty the other day about this. And I said the reason that we use a PIN diode for a varactor in microwaves is to increase the capacitance. Well, that's just the opposite. They will go to a pin structure because they can't realize a low enough capacitance. You can kind of think of it as you make the I layer thicker, it's like separating the plates of the capacitor farther, and so the capacitance goes down. So sometimes they'll go to a PIN structure just so they can get a tailored capacitance at a certain frequency range that they can't ordinarily get. So the pin is quite useful. It becomes several other diodes depending on how you make it. Another nifty device, and I don't know if Don Hope talked about this one or not, I don't recall, but tunnel diodes. Tunnel diode is another application of a PN diode again, but it differs from a PN diode in that the junctions are extremely highly doped. They use the term degenerately doped. And what happens is the characteristics of the diode change remarkably. what we end up with is a DC characteristic that looks like this. Now I will try to attempt to explain this without any great depth, and I'll let Jack and the other guys check me up on this. What happens is we have a phenomenon called tunneling, which I'll try to explain with an energy diagram next. But we have a tunneling current which starts to flow, and you remember that the diode in equilibrium, there is an equal and opposite current at equilibrium to the building potential generates a forward current and a reverse current, and they're of equal magnitude such that they cancel each other out, so that the device doesn't act like a battery when it's sitting there. It's at zero bias, the diode is truly at zero potential. Okay, what happens is as this tunneling current, and I'll explain what that is in a second, starts to increase with the application of forward bias, you go through a point and reach a peak where the reverse current has gone to zero. Then as the tunneling continues on, the tunneling current now causes a decrease in current flowing. It tends to flow in the opposite direction through the junction. And it'll reach a point where the normal minority carrier injection across the junction takes over, and the diode starts to conduct in its normal forward characteristic. What this characteristic gives you is a negative resistance region. Now what's that good for? Well, negative resistance can be used to sustain oscillation. You know, when you build an oscillator, the idea of making it oscillate is you put in a 180-degree phase shift. This causes it to be unstable. The device can oscillate, and you usually match it with a impedance that's less than the magnitude of the negative resistance to sustain oscillation. This is kind of the general rule of thumb. Another thing you can use this for is it sure works nice. You can picture this thing with a load line on it to square up signals. Actually, you can go on and on and on. This is a rather nifty device, and I've listed just some of the applications on the top slide. Amplifiers. Well, how could it be used as an amplifier? Well, that's kind of difficult to explain because of the concept. You probably don't know what reflection is yet. But what actually happens is that if we bias the tunnel diode into its negative resistance region, which is really its usable region, and we put an RF signal incident on that diode, the signal that is reflected is actually higher in power because of the negative resistance than the applied signal. And so we get amplification. It's sort of a two-terminal amplifier. And a little later, if we can get to it, I'll explain what we mean by reflection. Now, I said there was a phenomena called tunneling. What happens is the device is so heavily doped that as we look at the sides of the junction, and I believe this is the N side and this is the P side, we actually have the equal distance, or the what you call the balanced energy level, the Fermi level, actually lies in the conduction band on the N side of the junction and in the valence band on the P side of the junction. So what you have is above the Fermi level, you have unoccupied states. Below, you have occupied states. Same thing in conduction band. Above it, you have unoccupied states. And below it, you have occupied states. All right, so what happens is, at zero bias, this can happen. Some of these carriers in both sides of the junction are at the same energy level. Energy is the y-axis here. So what happens, or what the quantum mechanical phenomena called tunneling is that even though these devices are of equal energy level, some of these will overcome the barrier and manage to get into the other side of the device. In other words, some of these conduction electrons will flow into the valence band. The current is in the opposite direction, of course. Okay, as we forward bias the diode, we increase the number of electrons in the valence band, and there are vacancies at the same energy levels over in the valence band, in the conduction band, and they can actually jump across the gap. Now, the way they explain this, they say there's a high probability this can happen. The reason it happens is this displacement here is very, very thin. In fact, the junction on a tunnel diode in its negative resistance region is like 100 angstroms. So it's very, very small. And so the probability that an electron can travel from one side to the other is very, very high. Okay, in reverse bias, of course, it just tends to go the other way. Now, you see the little lines that are drawn, they actually represent the magnitude of the current that can flow. And as you apply a small reverse bias, you can see this component, excuse me, this is forward bias. I'm sorry, I got this all backwards. For some reason, I always like to have forward here and reverse here, but on this diagram, they're reversed. What happens here is electrons can conduct from the N region into the P region, which constitutes forward bias, because the magnitude of the current flowing in the opposite direction is less than in the forward direction. The same thing is here. When you reverse bias, now you have more carriers that can flow in the reverse direction, so the diode is reverse biased. I hope that's clear. There's probably a better way of explaining that, but without going into the in-depth physics of the thing. The tunneling phenomena is simply that electrons of equal energy on either side of the junction can travel to the other side of the junction. There's a high probability that they'll do this, and that effect is called tunneling. Now, in essence, on these negative resistance devices, which probably should be explained before we go into what's called impact diodes, the voltage is a function, or the applied field is a function of the voltage that's applied at the terminals of the diode. The amount of carrier flow controls what the current is through the junction. So what happens is as you apply a larger field, the carriers tend to saturate. They cannot move as fast as the applied electric field would dictate that they do so, because it's a tunneling phenomena in the tunnel diode's case. So what happens is the current actually lags the voltage that's applied at the terminals. And if they lag it at 180 degrees, if there's a phase shift, that much phase shift in the applied voltage, remember we're talking about applying an RF voltage now across the terminals of the device, you will get a negative resistance. A 180 degree shift is equivalent to a negative resistance. Okay, an impact diode and all the other diodes we're going to discuss are negative resistance devices also. IMPACT stands for, I'm going to show it up here, impact avalanche transit time. Okay. Why impact? Okay, Jack explained avalanche breakdown when he was talking about SCRs. What happens is you reverse bias your diode to such a point where all the carriers recombine, and there's a tremendous field potential that exists. And what happens is, as you now increase the reverse bias even further, some of the electrons, or carriers I should say, get sufficient energy that they jump and move across the forbidden gap. When they do so, they crash into another electron hole pair, causing two more to be produced, which in turn hit two more, which in turn hit two more, and pretty soon you have a multiplication effect, and that's called the avalanche multiplication effect. And the device goes into avalanche breakdown. I'm sorry. All these carriers constitute a very large current. And as you reverse bias the diode even further, just slight changes conducts an infinite amount more of current. They call the act of these carriers hitting an electron hole combination and breaking loose impact ionization. And so what we're really saying here is that we have a diode that is biased into avalanche breakdown in its normal use. It's a normal diode, for example. Could be done this way. Then what happens is we apply an RF voltage, and again, the field and the current become 180 degrees out of phase, because what happens is the carriers can only move so fast. They go to a certain velocity and they saturate, and they don't keep up with the applied voltage field. And so we get the current through the diode actually will lag at about a 90-degree angle from the applied voltage in this case. Well, all they have to do is design the diode such that the bulk of the diode supplies the other 90-degree phase shift, and they get a 180-degree phase shift for a negative resistance. They don't have to do that in a tunnel diode, which is really unique. There are two types of constructions of impact diodes. They have simply the single drift and the double drift, and all that means is that One of them is an N plus N P P plus to get a double drift, and a single drift just has a single N layer between the N plus and P plus. We get one avalanche drift zone between the P and the N in a single drift, and actually two in the double drift device. Look at my notes on that. Okay. This is kind of an ideal set of waveforms to show what I was talking about when it was we apply the diode voltage, which is an RF signal. The device is DC biased into reverse breakdown. And what happens is we get a sudden charge buildup that lags the applied voltage by 90 degrees. Pi over 2 is 90 degrees. The diode is so designed, I showed you the N region. The N region causes a transit time delay, and hence the term impact avalanche transit time to make up the full story how the device works. Supplies another pi over 2, and we end up with 180 degrees of phase shift, and so we end up with a negative resistance. And this just shows from this point on the induced current, and you can see that it's out of phase by 90 degrees from the applied voltage. What these things look like when they build them, they're actually built upside down. They start like any conventional device with an N plus substrate, and they grow an N, a P, and a P plus. Of course, it's a double drift device that I'm showing here, but all we have to do is forget about the P layer to talk about a single drift. They then reduce the thickness of the substrate, metallize both sides of it, and now they plate a very thick heat sink at the P plus contact. It's not shown here, but the metal on the front now is delineated, and then thicker metal for contact is plated, and then the devices are etched into a mesa type structure, actually upside down. This device is then turned upside down to be used in the circuit. Now, why the mesa can be explained from the phenomena that the same phenomena that requires a lot of our transistors to be made with an interdigitated geometry. There's a current crowding effect which is minimized in a mesa structure. And you will find that most microwave devices, I say most, I don't want to say all because somebody will prove me wrong, are constructed with a mesa type construction to avoid the current crowding effects that happen in a planar type arrangement. What happens is all the charge, all the conduction occurs at the periphery of the metallization pattern rather than, or actually the shape of the junction, rather than in the middle. And this tends to minimize that effect. So the reason that there's two of them shown is that this particular device that the slide was derived for used two of these in parallel so that it actually got much higher negative resistance. Now there are other variations, and I'm just going to show you these so you know the names. I guess we could go on and on. I'm sure there's others. But we have a device called a TRAPIT, which is a trapped plasma avalanche triggered transit. Okay, that is very similar to an IMPAD diode. The difference is it's like an IMPAD diode that's normally operated in pulse mode. And what happens is the RF is pulsed, and each pulse is short enough that the avalanche carriers don't have a chance to keep up with the applied pulse width. And so what happens is they keep pulsing this thing much faster than the carriers can flow just one time, and we end up with the charges being trapped. They don't go to an equilibrium state. It's kind of like sending a shock wave through the device as it's being reverse biased. And of course plasma normally means an ionized gas. In this case it's ions trapped in the silicon that can't redistribute themselves to neutral levels. And the reason for a TRAPIT, now that they have IMPADs, the TRAPIT is capable of much higher powers, but it has to be under pulse conditions. A device called a tunnet, a tunnel transit time. You can almost guess what that is. Now it's kind of a combination of a tunnel diode and an avalanche breakdown, except they don't have to bias the device in avalanche breakdown. They use the same effect with the tunnel charges. They can't keep up with the applied field. They lag it. They operate this thing under pulse mode to get very, very high powers. There's something called a MITAT, a mixed tunneling and avalanche transit time. Now, not only do they take advantage of the tunneling phenomena that occurs in a very highly doped device, but they also run it into breakdown at the same time and just thoroughly complex the matter. But these are used because they probably generate the highest power of all these. And there's only one group that I know that uses them in the entire world, and that's Hughes Aircraft. They use them in their satellite transmitters. As a matter of fact, the Voyager that went out and sent back the beautiful pictures and all that of the Saturn rings, that they actually used the MITAT to generate the transmitter power. It's kind of neat. One more. I have a device which is structured as an N plus N plus negative resistance device. It's called a gun diode because it uses an effect that was first explained by a man named Gunn. And can I explain this question now? Find it here. Okay. These devices are generally manufactured out of gallium arsenide and indium phosphide. And the reason for that is, in gallium arsenide, there are actually 2 conduction bands, which is kind of unique for that. And indium phosphide, same thing. And what happens is under bias, the mobile carriers from the higher conductivity band can be induced to go to the lower conductivity band. We apply more field potential to the lower band, and so they can accept the electrons. Okay, what happens is, again, we get a negative resistance effect because as you apply a voltage to this structure, operating, well, like I say, this is in gallium arsenide or indium phosphide. Again, the velocity saturates on how fast the carriers can go from the one conduction band to the other conduction band. It can't keep up with the applied field. Again, the carriers determine what the current is. They are the current. The electric field is directly proportional to the voltage applied, and so because they lag it, they can design the device so they get 180-degree phase shift, and again, you have a negative resistance. We can use it for the same things. But mostly what these are used for is power oscillators, sources for transmitters. Again, this device is typically used in a pulsed mode. The phenomena causes an excessive amount of heating in the device, and they could not get the heat out of the device if they ran this in a continuous wave type of form. So they do operate them for that reason in pulse mode. A LISA device is a gun diode, and that stands for limited space charge accumulation. All it says is that they operate the gun diode in a certain form. They take the applied RF voltage that they're using to get power amplification or get negative resistance. In this case, they're hitting it with an RF source to produce a harmonic, which is a power harmonic, but it sustains a pulsed oscillator. Like I say, you can get very complex in how these circuits work, but it's pulsing this thing into oscillation. And what the LSA device, what this all means is all they do is they distort the applied RF so it has a larger positive swing. And what this does, this keeps charge from accumulating during the negative part of the cycle. By going more positive, it dislocates the charge far enough that it doesn't have time during the negative swing of the cycle to be redistributed, and so the only effect it does is gives the gun a little higher efficiency. Otherwise, there's really no difference. One more device, actually 2, because I found another one after I made this. It's called a Barrett diode, a barrier injection transit time. Now, Al Aselmar drew an analogy to this, which I didn't think of, but it's exactly what it is. This device is no different than a PNP transistor, except it's optimized for this effect. That you look at a BV-CEO characteristic. What happens is one junction is forward biased, the other junction is reverse biased. And in very general terms, what happens is, as you increase the reverse bias, the depletion region created by this reverse bias junction starts to approach and overlap the forward bias junction. And what it tends to do as you increase even more forward bias, and by the way, this does have an anode and a cathode. It is truly called a diode. It tends to cause the potential barrier on the forward bias junction to become smaller, so more charge can overcome it. So what happens is the charges are injected, they get across, and they hit this high field region of this reverse bias junction, and they go lickety-split across that junction. Again, they go to a saturation velocity. Can't keep up with the applied voltage. And again, you get a negative resistance. So once again, we have another negative resistance device. Now, if they come in and they stick I believe it's an N+ layer in here, they end up with a device called a DOVET, a D-O-V-E-T-T, which is a double velocity transit time device. And I guess we can go on these devices. In essence, now we got two regions doing this instead of one, and so the two tend to sum up and give better efficiency, and that's the only reason for it. Anyway, I hope you at least have some understanding of how those devices work. I'm not an expert in them, I'll admit that right away, and I'm sure it shows through. Something a little bit nearer home. Microwave transistors, finally. As I said before, the difference between a microwave transistor and a low-frequency transistor is generally the geometries are shrunk down. They're much, much smaller. Again, the higher doping, but you can have a low-frequency transistor that's just as high doped, so that's really not a distinguishing characteristic. Okay. Generally, a few comments about what a bipolar, how it's built up. They're generally NPN transistors. In fact, I could say almost always they're an NPN transistor. The reason for this is, and it's in silicon, I'll qualify that in silicon. The reason for this is there's a much higher mobility in N-type silicon, and so the frequency performance is much better in an NPN type. Okay, generally the base region, Bill Dawes mentioned when he was talking about transistors and how thick this base region was, he mentioned that when you get to microwave transistors, you're only talking about 0.2 of a micron. In general, it's always a submicron type device. Well, we have devices that we use, and I use them at low frequency, as a matter of fact. They're only 1/10 of a micron. And I would imagine there's probably some that exist that are even smaller. But they're usually very, very shallowly diffused to get the high frequency performance. Let's see if there's anything else I wanted to say. Okay, in field effect transistors, we have basically two types that are used at RF, although there is a JFET, and I mentioned on the slide. JFETs aren't used that much anymore, so I'll just mention they were used, but they've been more or less replaced by one or two different types of devices. Now, a MOSFET, which is a metal oxide semiconductor field effect transistor, and a MESFET, which is a metal semiconductor field effect transistor. In the MESFET, which is the one capable of operating I guess right now up to 20 gigahertz, kind of the rule of thumb on that. You have let's say the device is built by putting a very thin N-type gallium arsenide layer on, in essence, a semi-insulating substrate. And what this does, and why gallium arsenide is so much better at RF frequencies, is number one, the semi-insulating substrate gets much lower resistance and parasitic capacitance than a bipolar can give. The other benefit of gallium arsenide, and related compounds I should say, is that the mobility of the carriers in gallium arsenide is about 5 times greater than it is in silicon. And so we end up with a much lower operating voltages and, again, a much lower on resistance when the device is on. The MESFET does not have to be built on gallium arsenide. There are silicon MESFETs, but for the highest frequency performance, they are built on gallium arsenide. And I also mentioned the MOSFET. Mars will talk about the MOSFETs tomorrow. A MOSFET is capable of high frequency performance, but generally, I say generally, as soon as you say it always is, it's not true. Generally, they're used a gigahertz or less. There's a technology called VMOS, and takes advantage of some of the power dissipation problems that they have. Beyond that, the only thing I can say about a microwave transistor is it's not different in any way from a low-frequency transistor. It's merely optimized with smaller geometries to work at microwaves. And we, right now, I think the technology says that you can use silicon up to about 8 gigahertz. And if you want to go above 8 gigahertz, we go to a gallium arsenide FET type device. Mars?
Yeah, this conference that we were at, we saw some still with that transistors that went all the way up to 70 gigahertz.
70.
Yeah.
Okay, now they're 70 gigahertz.
They're going up higher and higher.
Generally, the rule of thumb is that the gate width, right? I have the terminology right. It always seems the opposite. The gate length. I told you I'd get it backwards. The gate lengths are usually sub-micron, below a micron, to get to 20 gigahertz performance. I guess they're getting the gates even smaller. And get to 60 gigahertz or whatever. Anyway, I want to show you some. Unfortunately, I didn't have overhead transparencies on these. On the bipolar transistors, we have small signal as well as power devices. The small signal devices are usually operated as a linear device, usually Class A, but they don't have to be. But for what we use here at Sandia, they are. And we have fairly straightforward methods of characterizing those devices. When we get into the power devices, in order to get the efficiencies that we have to get at these frequencies, they're normally operated in a Class C mode or a Class AB at least. And of course, here we use them for radar fuses, and so they're used in pulse mode. And so the power transistor kind of, and I think the optimum idea of this one was to get it to 50 ohms, wasn't it, Mars? Or as close to it as they could possibly get, so that you didn't have to do a lot of tuning external to it and so forth. And we can go as complex as this device, which actually has not only semiconductor elements, but a bunch of them in parallel, and they're all connected through MOS capacitors to the external leads. Now, what does all that do? That's the question. Well, the devices are actually tuned circuits. We have paralleled a bunch of transistors. In this case, I don't know how many cells are in this one, 16, I guess. They are all parallel tuned, and I think the optimum idea of this one was to get it to 50 ohms, wasn't it, Mars? Or as close to it as they could possibly get, so that you didn't have to do a lot of tuning external to the device to drop it into a 50 ohm circuit. And what happens is each bond wire forms a transmission line. Lower frequency guys would model it with a single inductance, but they are a transmission line. The CMOS capacitors form actually a low-pass filter, or a capacitor to ground, which is used as part of the filter. If you remember what a thing called a Chebyshev filter, I think there's a tendency to design these to be an N-element Chebyshev filter. And what it does then is it matches finite impedances on either end to 50 ohms. So I'll just pass this around so you can take a look at the complexity. And then I also have a couple others of lesser power, and you can just tell by the complexity of the device which one is a lower power than the other. As you tend to parallel more die, you're handling more power. But they're kind of unique in that they're really a small hybrid rather than a transistor. And this is, just to let you know, this is what Mars and Charlie have to work with all the time. Fortunately, I only have one of those, and it's very simple right now. Okay, the other thing I want to talk about is MMICs, monolithic microwave integrated circuits. I think in the industry today, these are built out of silicon and gallium arsenide. Silicon's much lower frequency, but what they are is a true integrated circuit with all the microwave matching networks and so forth. And ideally, what you end up with is some circuit function on a single slab element of silicon or gallium arsenide that is an entire circuit matched to 50 ohms, matching networks and everything. Ideally. Wish it always worked out that way. The only thing I want to say on these is that right now, Mars Armendariz and John Saylor are developing our first monolithic device, but this is the future of microwave devices, from what I see here at Sandia. Probably the only exception to that will be the varactor diode. It's probably the only element they will not be able to realize on the same single substrate. However, I fully expect in about 10 to 15 years that we'll put a whole radar on one piece of gallium arsenide. And so I want to mention that. All this other stuff you can forget.
They're doing away more with diodes, and they're going into three-terminal devices like the field effect transistor. Because with the three terminals, you can do more things, and so they'll probably find a FET that will do the same thing that a Barrett does.
I see that it's already 10 o'clock, so I'm going to go through this real fast on the packaging. I think we'll just stop there. Microwave packaging is distinct from other transistor packages because, first of all, we're always using the device in some sort of a controlled transmission line environment. In other words, I kept talking about 50 ohms. Everything was matching 50 ohms. This is kind of the industry standard. There is a 75 ohm system that is used in some places, but the majority of the RF test equipment that's built is a 50 ohm characteristic impedance. And again, the device mechanically has to be compatible with a strip line type or waveguide cavity type of device, and I'll show you just some quick outlines are in your notes. But the reason that we go to the package style that we do, we want a controlled or low loss parasitic on the package. Again, compatible with 50 ohms. It has to be hermetic and it has to be rugged. And to do that, we go to styles that look something like these. These are some Hewlett-Packard, but it represents some of the common packages that we do have. And I'll pass these around so that you can get some idea of what these things actually look like. But they're all characterized in a strip line package as being a flat leaded and radial geometry. All the leads go out radially, as opposed to the TO18 can that Al Osamar showed you or whatever. Now that doesn't mean that you can't use that package for RF and microwaves. However, generally the parasitics on that package aren't as well controlled, and let's face it, aren't near as good when you get to the 10, 12 gigahertz area. So they go to these. They're usually made out of alumina oxide or beryllia to get the heat out. This is some more examples of some shapes. These are cylindrically shaped, incidentally, with a threaded stud. It's kind of hard to see. The quality of the slide isn't that great. And these are the type of things that I referred to as cavity or waveguide type packages. There is a sample in that box that's being passed around of this package right here. It's a small cylindrical package that's only about 50 mils in diameter. So you can see how small they go. Some of them aren't as big as some of the chips they use at low frequency. One in the aluminum foil, the TV dinner device. Okay, I mentioned in the introduction about beam lead devices. This is a PIN device, a PIN diode. And it's a beam lead, and it's a MESA construction in kind of like a planar package, which is kind of neat. But the problems that we've had with the beam lead devices on the low frequency devices don't manifest themselves on these because they are MESA. To get the capacitance down on the diode, the anode beam is actually supported by a solid fillet of glass. And you might say, well, that's kind of tricky to make these devices. And what they do when they're in the wafer farm, and here's the top view, they actually etch out the silicon in these squares and then fill them with a spin-on glass prior to putting the metallization on. But you can see the eye layer of the device, and it demonstrates that there is a high temperature nitride and an oxide passivation layer for reliability. So this device is pretty well hermetically sealed. There's actually, I wish I had an overview of another device that Hewlett-Packard has of a similar nature. This is a HP device where the entire junction is sealed in the glass. The glass is on all sides. The reason this device doesn't suffer from the problems that the low frequency devices do, what you're trying to keep from happening is having this beam, this metallization, going to the anode lead, touching the substrate, which in this case is the cathode. Well, there's no problem here because the entire beam is supported by a very, very thick glass layer. If for some reason this metal makes contact with the substrate, you don't care. You know, if it begins to form gold, silicon, eutectic, whatever. That can only make the ohmic contact better. So it's a very reliable packaging scheme. This is what that device, same device, this is a picture of it in relative size. See, this is a pica small I off an IBM Selectric typewriter on very good bond paper. That's why you can see actually see the filaments. And I'll pass that around. We buy these devices in a farm called an as-ist array, which I just happened to bring one along, and I'll pass the picture around. This is the same diode in this picture. I'm going to fool you here in a second, pull a switch on you. But what it is the wafer is mounted in wax on a sapphire quartz. This happens to be a quartz disc. And then the devices are chemically etch separated. And what you end up with is a very rigorous pattern, how they would find on the metal mask to expose them on the wafer. And you can automatically probe these devices to test them. So it's a very unique way of doing this. This is kind of a blow-up photograph, what they look like. I switched diodes. It's an equivalent diode, but this is a Texas Instrument device. And it shows you all the devices in the array, and you can see the beams. The face side, the top side of the diode, I'll put my pointer. Oh, I took it down. Sorry about that. The top side, there's only about 4 ways you can put it up here. We'll go through all 4 of them. The top side of the diode is this side, the side that you're seeing here. These devices are actually upside down. You're looking at this side. So the active regions are down in the wax. And if you look at this picture, you'll see some vacancies. This is just to show you what happens when they pick a device out to do a sample test. In order to do some testing, because it's a beam lead device, it's kind of hard to heat those things up and run them at 125 degrees C. All the wax has tendency to kind of flow and all the devices become disoriented. So they pull the devices out and they actually bond them into a package. One of these packages that we're passing around, as a matter of fact, usually that 100 mil with 2 leads. And it just shows that they can be pulled out of the wax without disturbing the alignment of all the surrounding devices. This is an actual as-ist array, if you'd like to see one in the flesh, so to say. Okay, I was going to talk about testing, but since the time is really up, I just want to know if I guess I can entertain any questions right now.
Who does the probing on these? Do we,
Both the vendor and Bendix. The vendors, by the way, are right now for the microwave diodes primarily Hewlett-Packard on the beam lead devices. We have frequency sources as a Varactor vendor for us.
What kind of probe equipment they use for that?
Yes, I do.
What-
They use a PR100 TAC Teledyne.
oh.
At Hewlett-Packard, they use electroglass. And they use Kulicke, no, what is it? I can't remember the name of the firm who builds up the probe cards for them. But they're right down the street from Hewlett-Packard in Silicon Valley, and they build the cards up for Bendix and for Hewlett-Packard on the different equipment.
Does Jim Meyer's outfit do this similar work?
They don't handle beam lead devices, so.
Oh.
In fact, they don't handle diodes. They're thinking about getting in that business, I believe, but first they're going to get in the small signal transistor business there. Exclusively. He's talking about Power Hybrids Incorporated in Torrance, California, incidentally. And these devices are all built by Power Hybrids Incorporated. Any other questions? What I would have done was I'd like to have gone into measurements and what an S parameter was. You always hear us talk about S parameters. And our big mysterious machines. And by the way, you're all invited to come to our RF lab and we can show you. We have big mysterious machines that look like these. This particular, these are all called automatic network analyzers. A better name for them is S parameter measurement equipment, I think. Be a lot clearer. But the reason they're called network analyzers, we model 2-port devices, transistors, diodes, filters, capacitors, you name it, all as 2-port devices and call them 2-port networks. So They coined the name network analyzer for these things. The old 8542, which was quote-unquote replaced by the 8409 boat anchor, and now the 8510, which I'm happy to say ours finally got on order Friday, which is really nice. All Hewlett-Packard. Hewlett-Packard kind of monopolizes the market on this, I think. They have the leading edge on the technology. So, you know, anytime you're invited to our lab, and we'll try to explain, right now we could say we could demonstrate for you what how an 8409 works if we could just get it working ourselves. It'd be really nice. The other, for power devices, we have the little problem that the automated network analyzers are not capable of the power levels that are required to test those devices. So we go kind of to an indirect approach called a load pull tester. And it never looked like this except the day it was delivered, right, guys? This neat. But what in essence it is, we're going in the back door. Instead of measuring what the device is, we're presenting mismatches to the device with a programmable tuner, a computer, there's memory, a disk memory, and a computer through interfacing, and a controller controls a line, which is kind of hard to see on this, which is nothing more than a tuner, and it presents a known impedance to the device. We can program it. The line, the tuner, which is a kind of like a double slug tune line, is modeled, and from the model we know precisely when we position the slugs along the line what impedance we're presenting to the device. And from this we plot something called load pull contours on the Smith chart, which I wish I could have explained. That looks something like this. This is actually of the tuner itself, various degrees of mismatch. And what all Smith chart is corresponds to reflection coefficients from 0 to 1 at 360-degree phases. And there's a little equation that relates that to impedance. And so there's conformal mapping of the imaginary part of impedance and circles of the real part of impedance. And that's all Smith chart really is. And so here is I guess the right term is a loci of points that for a given power level or mismatch condition that device would lie on. And so it actually gives us a contour mapping of the device. From that we can go tell the designer, hey, don't design right here if you want that power. Generally what happens, these are of the tuner themselves. I couldn't find any nice idealized curves with devices. We've never got any of those yet. But generally these curves may be all adjacent, what's the term, touching each other. And so you end up with kind of a cliff condition where if you designed right on the edge of the cliff and your impedance mismatch was just that direction, you'd fall down the cliff and you'd go from lots of power to zilch pretty fast. So what we do is we map the devices and tell the designers, hey, if you want this power, then you got to stay, let's say, in the area of this circle. This would represent the limit, and anything inside that circle would be a greater than power. We also can do things like efficiency. I don't think you've ever done them, have you? Efficiency curves for the device, and a little variable called return loss, which is the same as reflection coefficient, just expressed in other terms. That's all I have. Before you leave, Dave asked me to pass around a roster and have everybody sign a roster today.